3, 2, 1, it says, and it's time to go. We've only got 3 more videos left, people. So I'm going to put that down. 3 videos. And you can probably tell there's some excitement in my voice when you hear about that. So, superstars. We're going to be superstars today and get it done. Talk about 7.2, about linear systems. Now, this particular section, or sections that we're going to talk about, revolve around finding solutions to linear equations that have, in this case, 3 variables or even more than 3 variables. And those systems of equations with 3 variables means that you're going to have 3 equations to solve them. So the number of equations that you need and the number of variables that you have to coincide with one another. So if you're going to solve something that has 4 variables, you're going to need 4 equations to solve it. And that particular solving location, instead of being an ordered pair, which it would be if you had just an x and a y concept, that'd be just this x and y. As soon as you end up with 3 variables, then there'll be an x, y, and z concept, or better yet, an ordered triple. Now, these equations that have 3 variables are really representative of equations that we would see in systems, mainly because they're drawn on 3 different axes. So an x-axis, a y-axis, and a z-axis, and they give you a point that's based on x, y, and z. So you're talking about 3-dimensional coordinates or 3-dimensional lines that are being drawn in that space. Now, if you have a true ordered triple, and it's said to be a solution to the system of equations, then that ordered triple must satisfy every single equation, meaning that those are where the 3 lines all cross one another, or that ordered triple satisfies each part of the system in its own right. So to check to see if something is a solution to it, you would just want to plug the value in to the originals and see whether or not it satisfies the equation and makes the equation true or not. So in this case, something like 2 plus -6 plus 2 would be an answer of 4, and that'd be -2. It would satisfy the first one. Now, the problem is that it can't just satisfy one. It has to satisfy all 3 of the equations, and if any one of them fails, then it's not a true solution to the system. Now I'm just going to check these other ones. So it's 1 plus -2 plus 1 equal to 0, and it is. That one checks out. And then the last one, 5 times 1 plus -2 minus 1, turns out to be 5. And that's -3. That's +2, I think. I'm going to check my work there again. 5 minus 2, which is 3, minus 1 more is 2. Yeah, it ends up failing this one, and you'd be able to say that's not a solution to that particular deal. So make sure that when you're checking your ordered triple, that it turns out that it solves all 3 of those particular deals. Now, if you were given the triple, that's easy. You just have to plug and chug kind of idea. But what if you're given the 3 equations and you're ultimately asked to find the ordered triple between these ideas? Now, that entails using a couple of different techniques that you can use. One would be elimination. We love to stack things up and actually use elimination to solve them. Or maybe you might use substitution. This would probably be my least favorite one to use. We've done 2x2 systems before. You did that in Algebra 1 and then possibly in Algebra 2, where you stacked them up and found it. Now we're going to talk about how would you stack up 3 of these possible deals and do it. Well, the technique that's used here is what I would refer to as not just elimination, but double elimination is what this is referred to as. And to do this, you'll have to do a combination of the 3 different equations in sets of 2 and find I call it a keeper concept. You get a keeper, a double keeper method, and you get a keeper equation, and then you eliminate those equations a second time. So there's two sets of elimination. Now, I'm just going to label these three equations as like equation number 1, equation number 2, and equation number 3. And I'm going to find a way to eliminate the same variable in both equations twice. So let's say we were looking at these two here, and ask yourself which one seems like the easiest one to eliminate. Well, the one that matches up probably the easiest is the y's, and I'm going to go for a 2 and 3 combination. That means equation number 2 and equation number 3. And I'm going to write equation number 2, which is x plus y plus z is equal to 3. And I'm going to write equation number 3 underneath it, but I'm going to make this elimination an addition. And if I ran a negative through this entire deal, like you would do in elimination, this would be negative 4x minus y plus 3z is equal to negative 2. Now make sure that when you're multiplying an entire row by a value, that you end up multiplying the entire row. Don't forget of what you're trying to do. Now, if I add these columns together, would be negative 3x, eliminated the y, and I'd end up with positive 4z is equal to 1. This particular equation that's written right here is what I would refer to as a keeper. This is keeper number 1. And you've done a good job of eliminating a single variable and got yourself an equation that doesn't have that variable associated with it. Now, the problem is that for you to use this keeper, you need 2 of them to be able to eliminate again so that you can get one single variable. Now, what we're going to do is we're going to look back at our original equations and eliminate the value of y a second time. Now, this time around, I'm going to use equation number 1, and I'm going to use equation number 2, a different combination other than 2 and 3, but this time 1 and 2. And I'm going to use, let's say 1, which is 2x plus 3y minus 2z is equal to 3. But this is going to need to be multiplied second row by a value of negative 3 so that I can eliminate the y again. So let's multiply that guy by negative 3. That's what my idea was here. And I would end up getting negative 3x minus 3y minus 3z is equal to negative 9. And that's the second one, second equation multiplied by negative 3. And now I can add those in an elimination sense. So negative 1x, eliminate the y again. Add these together is negative 5z is equal to negative 6. Now, this second equation that I got right here is the second keeper. That's why we call it double keeper method. And what you're going to want to do now, since this is a double elimination concept, is take these two equations and eliminate again. So we've got negative 3x plus 4z is equal to 1 is one combination, and negative 1x minus 5z is equal to negative 6 is the other. Now, as you can see, one of these definitely needs to be multiplied by a scalar multiplier so that you can end up eliminating the equation again. I'm going to multiply the bottom row by the easiest one, would be negative 3, and that would change this to a positive. So let's do a little rewrite here. Negative 3x plus 4z is equal to 1, and positive 3x plus 15z is equal to negative 8 or positive 18. And we'll end up getting 19z is equal to 19. And good job, you found one of the 3 answers, and that is that z is 1. Now, your ordered triple is going to have 1 as the z down here at the end. Now, how are we going to generate the other 2 answers? And this all comes from just a recycling of the question back into originals that make it more reasonable. So I'm going to recycle the 1 into either one of the 2 keepers. It would not matter. Negative 1x minus 5 times 1 is equal to -6. Well, that's -5 added would be -1. So -1x is equal to -1, or x is equal to 1. There you've got a second part of your 3 pieces to your ordered triple. And then last but not least, you could recycle those 2 answers into an original. And I always usually go for the easiest original. We've got 1 and 1 for x and y. And I think the easiest original would be probably this one. X and y and z all add up to 3. That must mean that y is 1 as well. So there's your ordered triple right there. Now, if for some reason you end up losing variables in your eliminations, which we've seen in the past, it will just mean that those 3 equations don't have an ordered triple solution. And if for some reason you get a no solution or an all solution case, you might be sitting in one of those particular cases. Now, an all solution is very rare, where you're basically talking about all 3 equations are the exact same thing. They're just multipliers of each other, where all the variables would eliminate, and you'd get 5 equals 5 or something. And that just means they're all the same line. If it turns out that you lose and get and end up no solution, like say 5 is equal to 7 in the end, and the variables will all disappear, then you're talking about 3 lines that don't have a solution that goes with them. Now, you probably remember that we've solved these orders of these systems in several different ways. Now, doing double elimination can kind of be a long process, especially if the equations were not 3 variables, but maybe 4. It'd be a triple elimination, and you'd be burning through paper trying to get it figured out. That's why we introduced an entire new concept of mathematics, and we called it linear algebra. And one of the things that linear algebra did for us is it allowed us to organize information into matrices, and those matrices were a nice, easy way for us to work on data. Now, one of those that you've probably seen in the past, this is a 2x2 system because there's 2 equations with 2 unknowns. And the calculator, you would enter it as a 2x2 matrix. And now one of the matrix solving techniques was that you took the variable matrix, not variable matrix, this is the coefficient matrix, and you would multiply it by the variable matrix, which in this case was x and y, and you would end up getting the answer matrix down here, be answer matrix on the end. Now, this might have been a while since we've seen something like this, but that would be like 2 and -7 and 3 and 8 would be the matrix that you would end up for the variables, multiplied by the variable matrix, which is x's and y's, and then that would be the answer matrix of -10 and 22. Now, your goal would be to move this particular matrix over to the other side right here, and that technique of moving it is not going to be based on division, but by using the matrix's inverse to figure it out. And once you got those plugged in, the answer matrix or answer matrix that you're looking for, x and y, would be the inverse of the variable or coefficient matrix multiplied by the answer matrix over here. Now, this is, I'm writing it out in terms of just kind of like what the operation is, because ultimately I would go to my calculator to calculate this particular question. Now, let me show you on the calculator how to do this, and we're going to be using a lot of this with matrices. So important piece here, and this is just kind of a reminder because I think we've seen this in a while. Second matrix is where I'm going to go to. Edit the matrix, which is a 2x2 matrix, and we would end up having a matrix of 2 and -7, 3 and 8. We've done this particular stuff in the past, so this should be just a reminder. So the matrix of the 2x2 has been entered. I'm going to second quit out of that, and I'm going to go back to matrix and make matrix B, which happens to be 2 rows by 1 column, so it's a 2x1, 2x1, and that answer matrix is -10 and 22. And if you have to slow this back down and go back and look at this video, I totally understand that. Let's second quit out of this. And when we go back into the matrix the third time, this time around, I'm going to be pasting stuff to the home menu. And I'm going to be like, okay, matrix A. And that's where this equation starts to really make a lot more sense of what we're trying to accomplish. We want to take the inverse of the matrix and then multiply it by B. So let's take that A, raise it to the -1, which is finding the inverse, and then go back into the matrix names and multiply it by matrix B. And that would give you the solution matrix. And in this case, the matrix would be 2 and 2. And that answer matrix that you're solving for right there tells you exactly what x is. X is 2 and y is 2 as well, or a coordinate of 2, 2. Now, this particular method right here, or matrix solving, works on the premise that the system that you're working on is a square system, meaning that it's 2 by 2 or 3 by 3 and so forth. And you can find the inverse. Now, there is another technique that we use, which is referred to as row reduced echelon. Now, Mr. Leesman and myself will probably remember row reduced echelon from Algebra 2, probably with not much wonderful feelings because we had to do it by hand. Now, your calculators can do row reduced echelon in its own right. Now, what you can do when I say a 2 by 2 system is that one that we had up above up there was a, I'll just write this system right here. And you would write the variable matrix as 2 and -7 and 3 and 8 the same similar way. But if I was going to do row reduced echelon, what it allows you to do is to paste inside of here the answer matrix. This is called an augmented matrix, where the answer matrix is on the end of the matrices. And this is what it ends up looking like for a system that's going to be done by row reduced echelon. Now, what row reduced echelon means, let's just kind of understand what it means, is it's going to reduce the rows into a way that you will end up with an inverse matrix, or an identity matrix is what it is. You get an identity matrix in the process. Now, what it boils down to is that there's ways to add and subtract the rows in some math, and we're going to skip that whole math concept until you can actually generate the row reduced echelon. You can make these numbers by adding and subtracting and multiplying and scalars and so forth until you end up with the identity matrix on one side. Now, the identity matrix can easily be identified because it has a diagonal of ones. That's what your goal would be. And you would find ways to make the -7 and the 3 turn into zeros and make these turn into ones. And whatever was left in these answers right here on the augmented part of the matrix would be the solution to the row reduced echelon. It turns out that these would be the number 2's down here on the end. And you would say that the answer is 2, 2 for that particular deal. Now, you can make these row reduced echelons in 3 by 3 or 4 by 4 locations. So you would have, like, say, an original matrix that was 3 by 3, so 3, 2, 1, and I don't know, 2, 5, -7, 4, 6, and 4, something like that. And then you would have your answer matrix over here, which would be like 11 and 14 and 6 or something like that. Now, your goal would be based on row reduced echelon, or RREF is what we call it, row reduced echelon form. Your goal would be to make a matrix that would end up having the identity matrix on one side, and then over here on the far side, it would generate the answers for coming up with that. Now, what's in between right here is a bunch of math. It's a horrible math. It's not fun at all. But the cool part is that our technology nowadays allows us to use the calculator to generate this row reduced echelon form. Now, let's try that so you can get the idea of what it boils down to. Now, first off, if you're going to take a system of matrices that looks like this, you have to first be able to write the matrix, augmented matrix that you're going to use RREF on. And it boils down to the same idea that it's coefficients and answer matrix all put together. Now, be very careful. Make sure that your original equations are in, I guess, reduced descending order of variables. If there's a variable that's missing, you'd want to put in a 0. So watch for those kind of things. This would be 3, -1 and 2, 6 and -2 and 1, and 2 and -1 and 3. And you'd want to make sure that your variables were in order, so that would work. Now the augmented matrix to that would be 7 and 8 and 8. And this is what your augmented RREF matrix would look like before you got started. Now, let's go to our calculator and ask ourselves, well, how the heck would you need to do that? Well, we're still going to be talking about a matrice. So you're going to want to go to matrix and you're going to want to edit this. Now, you're going to have to think about this. What size matrix is this? And remember, it's rows by columns is the way that we write a matrix. So this would be a 3 by 4 matrix. So let's put it in as a 3 by 4. We'll edit this guy to make it 3 by 4 and enter those values. So 3, -1. Oops, I need to go to. I need to use the negative key. -1, 2. And then it's going to go over to the last column for the answers of the augmented matrix. So watch that. 7 and 6 and -2. This part isn't really too tough. It's just data entry. 8, 2, and then -1, and 3, and 8, finally, in the end. Okay? Now, how are we going to get that particular matrix into that augmented matrix into RREF? Well, one of the menus that we haven't used really a lot when it comes to matrices is we have used names and to paste on the home screen, and we've used edit, but the one in between we've not really used that very often, which is the math part. This is where we can do some calculations on matrices and where linear algebra really starts to shine. If we arrow to the bottom of this particular deal, you'll see that there is an RREF. There is a row reduced echelon on this, and we can paste that on the home screen and do this particular math. Now it's waiting for some input here. So your RREF of what? Well, it only makes sense that it's asking for what matrix do you want it to do the row reduced echelon on. So I'm going to go back into the matrix and use the names menu to paste the matrix that I want to use RREF on and enter. And it does the row reduced echelon for you. Now, let's see what this answer really entails. We should end up with a matrix of identity on one end, and then the answer matrix will be the answers that are on the far right-hand column of this, which is 1, 0, and 2. And those constitute the answers for X, Y, and Z because they're put in that particular order. This is X, this is Y, this is Z. And your ordered triple would be a 1, 0, and 2. And that's where those three lines intersect. Now, you're probably like, wow, row reduced echelon is awesome. It does the job for us. And we invented that kind of thing because it's important to be able to find these coordinates of intersection very quickly, and computers can do them really, really fast. If you've ever seen video of, like, say, one of the space shuttles or a spacecraft trying to link with the International Space Station with, like, say, the actuator arm that connects the two, well, you're trying to intersect a arm that's in three-dimensional space with the spaceship, which is in three-dimensional space, and you want to find their intersection. Well, that's how the computer actually does that, is it's finding the vectors in each individual case and connecting those vectors into a solution. Okay. Now, you can also use RREF to help you find other kinds of pieces of information. And this one says, use RREF to help you come up with this. It says the following are 3 points on a parabola, and it says write the equation that represents the form of the equation that they are. So let's kind of like think about what they're trying to say. We've got these three coordinates, which are like -2 and 7. 1, 2, 3, 4, 5, 6, 7. Here's one of the coordinates, and 1 and -2. Down here is another, and 2 and 3. 1, 2, 3 is the other one here. And somehow there's an equation that comes down here and hits all three of these points. Well, how are we going to come up with the equation for that? Well, the equation is something that is missing an A, B, and a C. So we really do have three unknown variables: a quadratic variable or quadratic coefficient, a linear coefficient, and a constant coefficient that would be necessary to write the equation. Well, the easiest way to look at this is that every one of these coordinates is an x and a y. And if we've got x and y concepts, we could plug in the x and y in each one of these and generate an equation that has a, b's, and c's, but the x and y's have been filled in. For instance, if I plug in this coordinate, I'd be saying 7 is equal to a times -2 squared plus b times -2 plus c. And I could write that equation as 4a plus -2b plus c would equal 7. And I could do that in every single one of those questions. Let's try it again for the second one. It'd be something like -2 is equal to a times 1 squared plus b times 1 plus c. And that equation would be something like 1a plus 1b plus c would equal -2. And the last one would be something like 3 is equal to a times 2 squared plus b times 2 plus c, and ultimately an equation of 4a plus 2b plus c would equal 3. Now, the last thing I would want to tackle on this is a double elimination concept. Why can't I just turn this into 4, -2, 1, and 1, 1, 1, and this is 4, 2, 1, and the augmented matrix is 7, -2, and 3, and use RREF on that concept. Now, what I'm going to do is I'm going to pause the video right here. I'm going to allow you to input that stuff into an augmented matrix and then push your RREF and see whether or not you can get a solution for A, B, and C. Oops, sorry. A equals, B equals, and C equals, so that we could write the equation of the parabola. So pause right here. And Zango, there's the actual answer to the RREF. And ultimately, looking at that final column, we would get 2, -1, and -3. And the parabola that would fit those three individual coordinates would be y equals 2x squared minus b, or 1b, or minus 1x, sorry, we'll think about that, right? Minus 1x minus 3. And that equation would match those three values. Okay, pretty straightforward concept and not a big deal. Now, here's a quick question. What if in the row reduced echelon you end up losing a possible value in your identity matrix? Maybe it becomes 0, 0, 0 on the bottom. If that ends up happening, then you're basically talking about a no solution situation. So be very careful that you are looking for the identity matrix as with the diagonal ones on one side. Then your solutions are valid. If it turns out that any one of these rows completely disappears with zeros all the way across, then the identity matrix has been invalidated, and ultimately you'll have a no solution case. Okay, now here's a 4x4 matrix. This is just getting into the situation of can it get bigger and uglier? And yes, it absolutely can. You just get an augmented matrix with a 4x4 in there, and you'll come up with an answer for X and Y and Z and W. And instead of an ordered triple, it'll be an ordered quadruple. And that That can happen. You're just talking about 4 different parts to it then rather than 3. You're probably thinking, well, 3-dimensional space doesn't account for a 4th note, and technically it does, because you've got 3 dimensions based on length, width, and depth, but the 4th dimension would be a speed. You can start to think of 4th dimension concepts too as well. Linear algebra really starts to delve into these ideas. Now, I'm going to pause the video and figure out this particular matrix. You guys can come up with an answer for it, and we'll see what we come up with. And it turned out that the answer to this particular augmented matrix, which wasn't really that hard to plug it in here, turned out to be 1, 1, 1, and 1. Woohoo! That was pretty easy. Again, watch out if you end up getting a row-reduced echelon that turns out to be a no solution. And if you get a row-reduced echelon that is a no solution, you will end up with a row that turns out to be zeros. That is a no solution case. It also will turn out if you want an all solution. So that's a no solution case. I'm trying to remember an all solution or infinitely many. And I'm going to have to pause and I'm going to have to look this up because I can't. All right, looked it up, figured it out. A no solution would be a situation where you're dealing with definitely a row of zeros, but it turns out that there happens to be a number on the far side. And that number being like, say, the number 14 or the number 5 or something like that. That would be an inconsistent solution, or basically a no solution, generating that one or two of the lines would actually be parallel to another one. If it turns out that you get a row of zeros, but the augmented part turns out to be a 0 as well, this would be a consistent solution, meaning that the 3 lines would have an infinite amount of answers because they lie on top of one another. So that's the difference between what you'd be seeing for a no solution and an infinitely amount of solutions, okay? Could you make up a system with 3 variables and 3 equations that has no solution? For the most part, pretty much any 3 that you probably would pick will more than likely not intersect and make a no solution. It is very, very hard to make 3 equations that have a singular solution or a unique solution in one ordered pair. Most likely, if you made 2 equations that were multiples of one another, say, for instance, say you had one equation was x plus y plus z is equal to 10, and then you made the second equation 2x plus 2y plus 2z is equal to 20, and then you picked anything else for the other one, like say negative 5x plus 7y minus 3z is equal to my favorite number, 13, okay? These two, since they are parallel to one another, would definitely create a no solution case because they're basically the same line. So some real concepts here about finding a no solutions case is really common, actually, because getting 3 points to intersect in one singular unique point is actually relatively hard. Okay, that's the reason why the defense system for the United States can't shoot down nuclear missiles when they're on their way over from Russia. You're trying to hit something that's going 300-400 miles an hour, and you're trying to hit it with another rocket that's doing the same thing. That's 2 equations in 3-dimensional space, 3 equations in 2-dimensional space, and it is not an easy task. So the idea here is pretty self-explanatory when it comes to using augmented matrices and RREF, or even using double keeper method if you're asked to do that. Now, if you were in regular class, we'd force you to do that, but keep in mind that we want to work smarter and not harder all the time. And once you finish with this video, there are only 2 more videos left, and you're done with the semester. Woohoo! Good luck on the Math Excel, and be looking out for Mrs. Merzak's hints to the Math Excel. And get her done, people. We're very close.